So, okay, please, you're invited.
Okay. Hi, everyone. Thank you for the opportunity to speak here. My name is Ido Ben-Shaul, and I'm from the Applied Math Department in Tel Aviv. This is joint work with Lea Bal and Professor Nir Sochen. So today, I'm going to talk about the research we did addressing the problem is, can we solve the eigenvalue problem with machine learning techniques, and more specifically with neural networks? So the eigenvalue problem is an important problem in many image analysis tools and other fields. So we want to look at classical methods of solving these types of problems. So generally, if we have a PD or ODE with, say, Dirichlet boundary conditions, the classical methods use mesh to solve these problems. So we have some discretization of this field, and then given it, we approximate the solution on each of these subdomains, and then we interpolate between them. So it's either finite elements or finite differences or some interchange between them. So there's some problems with this notion, right? So one of the most prominent ones is that this is very dependent on the discretization. So meaning that if we split up the domain in a different way, we're going to have a different solution. So we take a different approach that's basically mesh-free, and let's see how we do this. So given an ODE or PD, we use a neural network to model our function. So given an input vector x, our network is going to output u of x. Okay, so let's look at the network architecture. So we use several fully connected layers with a tan-H activation. Now there's two things to notice here. One, because we have this closed form of the output, so this is just how the output looks, right? So we could calculate the derivatives of this function. We can actually find this operator, this differential operator with respect to the inputs. The second thing to notice is we use a tan-H activation function. Now, this is very important because we want our solution to be analytical. So using ReLU or leaky ReLU or other things that are very common in this field is less suitable here. So our training procedure goes like so. So we have a domain, and we sample points at the moment randomly from both inside the domain and the boundary. This is important because it's basically mesh-free, right? We could sample whichever way we want, and we're not confined to the grid like other methods. In this way, we're able to solve the problem on more complex domains. For more examples, you can look at Lea and Neil's paper at the bottom. And let's look at the training procedure. So we're looking at the eigenvalue problem. So we have L that's self-adjoint, and we're looking for all lambda I ui that are eigenpairs such that Tu, as defined here, is equal to 0. So this is Tu from before, and then we can look at the loss function we use. So the loss function has several parts. The first part is just using the fidelity of Tu, right? We want this these gradients to be, the operator on the gradients to be equal to 0. Now it's important we use L2 fidelity and L infinity. This L infinity is important in the proof of showing uniform convergence to a solution. Now, on the boundary points, we use just L1 penalty for the boundary conditions. We add another technical term for the normalization. This is just basically if u is an eigenfunction, then any scalar times u is also an eigenfunction. So if we want to converge to a specific one, we just penalize its energy to be a specific value. And then we add weight decay, something that's very common in this field of neural networks for better generalization. So let's look at an example. So if we have the 1D Laplace equation, the first problem we aim to solve is, given an eigenvalue, can we find its matching eigenfunction? So we have the known eigenvalue 4, and we have the boundary conditions, and we know the analytic solution. Of course, our approach is unsupervised, so we're not going to be using it to train, right? So we train a model, and then we can see the ground truth function versus the model output. So we can see it pretty easily learns this matching eigenfunction. Now, of course, most of the time the eigenvalue is not given, right? We want to find the eigenpair, both the eigenvalue and the eigenfunction. To do this, we use the Riley quotient. So the Riley quotient, as defined here, has the interesting property that if our outputs are close enough to the eigenfunction, then RU is going to approximate the eigenvalue. Here you can find a short proof with calculus of variations. So given this intuition, we can define TU to be the same as before with substituting RU instead of lambda. So let's look at our loss function now. So we have the same loss, except we add this final term because we want to find the smallest eigenpair. So we penalize the size of RU just with L2 loss. So let's look at our example again. So we have the Laplace equation. Now we don't know the eigenvalue, and we have these boundary conditions and the analytic solution. And we train a model to find this. And here you can see the progression through the epochs. So at the beginning, it's just random. And then it converges to this nice 2 over pi sine x function. We can also look at the Riley quotient. We can see that it starts out very big and converges to 1, which is indeed the smallest eigenvalue. Now, finding one eigenpair isn't enough. Usually we want several. So the next question we mean to answer is, can we find the m smallest eigenvalues? This task is much harder, right? So the model has to learn m different functions. So to do this, we have to alter our architecture just a bit. So now, instead of having one output, we're going to have m outputs, each one corresponding to a specific eigenpair. For each one of these outputs, we're going to use the same loss as before, except this gamma I. This gamma I term is going to bootstrap these different sizes of Riley quotients. Now, if we only use this term, we're going to get a model that converges to the same eigenfunction for every one of its outputs. To solve this, we're going to use orthogonality. So different eigenfunctions are orthogonal to one another. So what we just add this penalty term of the inner product between every one of the outputs per batch. In this way, we're able to learn different eigenfunctions that are orthogonal. So looking back at our example, this is the Laplace equation again, and then we have the analytic solutions. And here we can see, for example, m equals 4. Each one of the colors is a different output. So we can see first that it converges to this nice sine of kx function. So it's 1, 2, 3, 4. We can see it handles different frequencies in the same model, and it has no problem doing this. And we can also look at the Riley quotient, and it indeed converges to this k-squared eigenvalues. We can also generalize this to more. This is, for example, 5, with this very high frequency function. If we look at the Riley quotient, we can see its convergence. That in the beginning it oscillates a lot, and then it converges to these k-squared, just like expected. We also generalize this for two-dimensional problems. So we can see this low frequency convergence. It's able to fit these quite nicely, and also these high frequency functions as well. To conclude, we propose an alternative to classical methods using neural networks that's mesh-free and therefore able to fit more complex domains. We're working on more difficult problems in higher dimensions, and we're also working on different sampling methods using the current model outputs to sample in more, say, interesting areas to get a faster convergence. If you want more information, please see our papers, and feel free to send any questions if you have. Thank you very much.
Okay. Okay, great. Thank you.